For this particular video, I want to talk about refrigeration and how refrigeration works. And you should watch the other videos from YouTube before you watch this one. So let me go backward, previous and previous. The first ones are how does refrigeration work? And I've got two very short videos that I took from YouTube. And rather than using the YouTube links directly, I downloaded them and posted them to Canvas in an effort to make sure that they don't disappear if somebody who owns these videos changes things. So I normally do this in class to show you some things that will demonstrate the basics of refrigeration. But if you're watching this online, you might not have the in-class experience. And I think the very basics are quite useful to understand. And I will go through this multiple times in different ways to try to help you understand the process. Next is boiling water in a test tube. And I think this is extremely valuable to understand the concept of boiling. Everybody starts this class with the same thought. Boiling is hot. You boil things to make them hot. Well, yes, you put water in a pot and put it on heat, and the heat will make the water boil. But what did I have to do? I had to add the heat by turning on the burner. I'm adding the heat. And if you know anything about water, it boils at 212 degrees Fahrenheit or 100 centigrade, 100 degrees Celsius if you prefer. And as soon as water starts boiling, the pot stops getting hotter. Boiling is actually removing heat. Boiling makes things colder. And that is really hard for some people to wrap their heads around at first. And then all of a sudden, it makes sense. Think about it. You're out on a hot day and there's a light breeze. What can you do to cool off? You can put a little water on your face. And then as the breeze is coming by, even if it's a hot breeze, as the breeze is coming by, it causes the water on your face to evaporate, turn from liquid on your face to gas moving away. And that transition from a liquid to a gas removes heat. It had to come from somewhere because there's a higher energy state of gas, a lower energy state of a liquid. So when you move to the higher energy state, where did that energy come from? The only place it could get it was from the heat in the environment. And in this case, the environment is your face. So when water turns to gas, from a liquid to a gas, it takes heat with it. And whatever's left behind is colder. Think about that, wrap your mind around it. You watch the video, and what is the person in the video, the teacher in the video doing? Putting water that is way below boiling and putting water into a vacuum situation inside a syringe. Oh, actually, that should say boiling water in a syringe. Sorry. Edit. So when you're putting water into a vacuum, there's less pressure holding that liquid water together. Because boiling of a liquid, the change of a liquid to a gas, is a combination of what's the temperature and what's the pressure. The higher the pressure, the more that liquid stays a liquid, and it takes more temperature to overcome that pressure and turn into a gas. You're under high pressure, even hot water, way above boiling, can turn into and stay a liquid. So it goes way above 212 degrees Fahrenheit or 100 centigrade in a pressure environment. Now, I don't have a video for this, but do any of you have a pressure cooker at home? A pressure cooker is nothing more than a pot with a special lid and very heavy duty lid and a very heavy duty latching mechanism to lock that lid on so it can handle high pressure. So let's say I'm boiling noodles, and noodles boiling at 100 centigrade, the normal boiling point of water, take, I don't know, let's say 8 minutes for whatever type of noodle you're talking about, because it's at 100 centigrade. What if I put it in a pressure cooker? Now that water might be 150 centigrade or 200 centigrade, depending on the limitations of that pressure cooker. Now, any pressure cooker is going to have a pressure release valve, so you don't create a hot water bomb, which is very dangerous. Water at 300 degrees centigrade, boom, blowing up in the kitchen and going all over everything and everyone. So pressure cookers can be quite dangerous if they aren't designed right and used properly, and you don't have a functioning safety release or pressure release valve to keep it from going above its rated pressure. But what are you doing? You're keeping pressure on that liquid. So as the water starts boiling, the water vapor inside the pot is creating the pressure pushing back down. And at some point, that water, which started boiling at 100 centigrade, because there's no pressure on it yet on this pot, because I put the lid on in my kitchen. I put the lid on the pressure cooker in the kitchen. So when I first start, the pressure inside that pot's the same pressure as my kitchen. But the pressure goes up and up and up as that water starts to boil, and it goes from 100 centigrade to 110 centigrade and to 115 centigrade, and it keeps getting hotter. That's not what happens in an open pot without a pressurized cooker lid. If I don't have a way to trap and hold and increase the pressure, the water boils, the vapor goes away, it takes the heat with it as it goes away, and the water boiling in an open pot stays at 100 centigrade, 212 degrees Fahrenheit, and it doesn't get any hotter. The only way to get it hotter as a liquid water is to put more pressure on it. And is pressure exactly the same anywhere on Earth? Of course not. Here at sea level, we have roughly 1 atmosphere of pressure, pretty darn close to 1 atmosphere of pressure, and it can go up and down a little bit. We measure that with a device called a barometer, which is a weather device. And when the pressure gets a little bit high, we call that a high pressure zone. The weather generally is low winds or no winds, temperatures go up, high pressure tends to be warmer. Low pressure in the environment, the atmosphere around us, when we have a low pressure, that tends to bring in clouds, maybe rain, and some sort of weather system. But in general, we have 1 atmosphere of pressure within a very narrow range that controls our weather. What if I go to Mile High Stadium? I go to Colorado, Denver, Colorado. and I'm at about 6,000 feet or just over a mile high in the Rocky Mountains. There's less air pressure up there than there is in Salinas. Because there's less air pressure, water doesn't actually boil at 100 centigrade or 212 degrees Fahrenheit when I'm in Denver. So that changes the response of water to heat and its boiling point. So it changes cooking. I haven't seen it in a little while, but I don't look that hard anymore. But when I was younger, there used to always be recipe adjustments for higher altitude because it takes a little longer to cook those noodles in Denver. Not a lot. You might have to throw an extra 90 seconds on there, which, in an 8-minute boiling, 90 seconds, that's a minute and a half. That's enough to make a difference. And cooking times, even in the oven, where you think the temperature is exactly the same. Well, the oven temperature is, but the response to water in the bread or casserole or whatever you're doing in the oven responds a little differently. So cooking times aren't exactly the same. So let's get back to refrigeration. What are we talking about with refrigeration? Why am I talking about boiling water? The reason I'm talking about boiling water is because these two examples, water boiling, hitting 100 centigrade, and then boiling like crazy, and it never gets any hotter, is one of the fundamental principles in what's called a heat pump or refrigeration system. And the idea that when water boils, it takes heat away. And when gas turns back to liquid, it gives off the heat that it gained when it turned to gas. Excuse me. So things get hotter when they condense from a gas to a liquid. Things get colder when they go from a liquid to a gas. Again, think about this. Water on your face. It evaporates, you get colder. But if I'm in a hot environment and water is on me sweating, that makes it hotter. The water from the air condensing onto my face. If I'm down in Louisiana in the summertime, most any time, it's humid and that water in the air settles and forms little drops on your face. That makes my face hotter. What about your drink? Where does that water come from? I've got an iced tea sitting on my desk. Not right now, but I wish I did. Thirsty. Where does the water come from on the outside of that cold glass of iced tea? It came from the air. Now, the iced tea isn't cold enough to make the whole room cold, but it's cold enough to make that air that touches the glass, the outside of the glass, pretty cold. And as that air touches the glass, it is cooling down, giving up the liquid, or excuse me, the gaseous oxygen and turning into liquid, the gaseous water. I'm sorry. It's giving up the gaseous water that's in the air and turning it into liquid water on the side of the glass, giving up heat in the process. So that speeds up the process of my iced tea getting warm. Liquid to gas gets colder. Gas to liquid, water condensing like dew on the outside of my iced tea glass, gas to liquid gets hotter. One more time, think about the boiling water. I'm boiling that water and it stopped at 100. What happens when I turn off the gas burner? It immediately stops boiling. Because the boiling is taking away heat. Boiling makes things colder. Take a quick break and I'll show you some diagrams.